My name's Dan, and I'm a grad student in the physics department at NYU. And this isn't my normal kind of setting to give a talk, so you'll have to bear with me here a little bit. I normally speak at physics conferences where we definitely don't have microphones and that kind of thing, so that's very confusing. At those kinds of talks, it's always very interactive, so I don't know what it normally goes like here, but please stop me and ask questions as we go through, because it'll be more fun that way. Today I'm going to talk a little bit about my thesis research, which I'll explain, and how Python fits into that, and I'll introduce some cool code that I've developed through this whole process. This is my tagline on all the social media, that I write code for good in astrophysics. I'm in the physics department, I said, but I focus on astronomy. And I'm going to talk a lot about the particular part of astronomy that I study. But for all of my work and in my spare time, I seem to spend all of my time writing code. In my work, though, I study astronomy, like I said. And in particular, I study planets. And this is a beautiful artist's rendition of a planet outside the solar system that NASA published. And this is not what my data look like. It's not what I work with. I do data science. I guess we all do that. That's why we're here, right? And we can define it however we want. I'm in the physics department, but I'm lucky that I get to spend part of my time at the Center for Data Science, which is across the street at NYU. They let me hang out there, even though I'm not officially part of it. And most of my work is in physics, but I collaborate a lot with computer scientists and applied mathematicians, statisticians, and that's been very important for all of my research. Now, all astronomers do data science. And for many astronomers, that looks something like this, which is beautiful. But I've actually never been to an observatory. I'm not a real astronomer in that sense. My version of data science looks a lot more like this, where I'm cleaning up the shit that they had from the telescope. And sort of more specifically, I do probabilistic data analysis, so I write down a lot of math to try to clean up the shit. And so that's what I'm going to talk about today. So there are two goals for what I'm going to be talking about. On the schedule it said 50 minutes, I think. Can someone correct me if that's wrong? 50? Yeah, okay, great. So then we'll be able to cover both of these goals. So the first goal is to tell you a little bit about my work studying planets and convince you that they're super cool. Hopefully that'll work. And the other part is to demonstrate some awesome code that goes along with this, but is also more general and useful. And so possibly some people in the room might find it useful in their work. So I study planets, I said, but in particular I study exoplanets. And that's a sort of fancy astronomy word for any planet that's outside of the solar system. So these are solar systems that are orbiting other stars, not our sun. The ones that we study are all within the galaxy, within the Milky Way, but they're outside of our solar system. And as always, XKCD has lots to say about this. There have been many comics. Here's one from a couple of years ago, where he was drawing all of the known planets at that point. And so there are 786. And you'll notice it's maybe too small to see, but near the center there's a little box that shows our solar system. And one of the things to notice from this comic is that the solar system is pretty different. And there's this huge range of different planets of different sizes that have been found. But like I said, this was also a couple of years old. More recently, he did a more statistical plot like this, where this is showing sort of the range of planets that exist corrected for all the observational biases and that kind of stuff. And so what you can see here is that there's there's a huge range. These are drawn to scale, so they're huge planets that have been found. They're tiny planets that have been found. You see Earth in the center. There's some that are smaller, lots that are bigger. And the ones that are red are orbiting stars like our sun. And then the gray ones are not like our sun. They're cooler stars, and so they're actually very different. So the thing to take away from this is that there's sort of this huge range of solar systems that exist out there. And basically at this point, it looks like every star has a solar system orbiting it. So that's pretty cool. So this is my field that I work in. And I mentioned that his comic, the first one that I showed, was a couple of years old. So it was published in 2012 when there were less than 800 planets known. This is the number of planet discoveries per year. 2014, which is the last bin here, is a good year. We've discovered lots of planets. And so now the number is more like 2,000, and we have 5,000 candidates. And so that's pretty cool. And a lot of this big rise in recent years is due to something called the Kepler satellite that I'm going to be talking about in a lot of detail. And it was launched in 2009. And so that sort of started this big spike. So this is cool. We've found thousands of planets, and we've characterized them, and we see that there's this huge range of things. And I also said that basically every star has a solar system around it. And in our galaxy, there are hundreds of billions of stars. So why don't we have hundreds of billions of planets in this sample, only thousands? It's pretty cool. We've spent, millions, billions of dollars on this, and we've found a couple of thousand measly planets. And the reason for that is that exoplanets are pretty hard to find. And there are a few reasons for this. One of them is, so in astronomy, for I think obvious reasons, we can't really do direct experimentation. Anything that we do is going to be very indirect. Everything that we're studying is very far away. We're talking tens, hundreds, thousands, tens of thousands of light years away. And these are considered the closest stars. Another reason why planets are hard to find is that they're not very bright. So the sun is really bright, and at night you can see the planets with reflected light from the sun, but the planets themselves aren't very bright. So if you're looking at a star out in space, you can't really see the planet because it's right next to this really, really bright star. And so that makes things a little hard too. So again, it has to be very indirect methods that we find and study these planets. So there are basically two main ways that we study planets. The first one is called the radial velocity method, where you look at the motion of the star relative to you, and what happens is as the planet is orbiting the star comes a little bit towards you and then a little further away, and you see this wobble. And we've been able to measure the motion of stars down to meters per second. So that's like walking speeds, So that's pretty crazy that we can measure stars that much. But the most productive way of finding planets up to this point is called the transit method, and that's the only thing I'm going to talk about today. And it's pretty cool. So the basic idea of the transit method is that, let's say we're an alien looking in at the sun. It might look something like this. And if we're an alien in some other solar system and we're looking at the sun, we just happen to be lined up perfectly, we'd notice that once a year, the Earth comes in and crosses in front of the sun. Right? So you can imagine it's pretty hard to be lined up properly because you have to be just in the plane of the orbit. But by definition of a year, this is going to happen once a year. The planet's going to come and cross in front of the star. And actually, the geometric factor, so just happening to be aligned in exactly the right place, if aliens were uniformly distributed over all the stars, 1 in 200 of them would happen to be lined up in exactly the right way to see us. And so so if you are, you would see this tiny little change in the, you'd see this tiny little dark planet cross in front of the star once a year. And that would last for about 13 hours. Okay? Now, if you're really lucky, this alien might also see Jupiter, right? And so Jupiter's a lot bigger, and so it blocks a lot more of the star. But it has a much longer year, so this would happen once every 12 years. They would see Jupiter if they happen to be lined up perfectly. I think the number is something like 1 in 3,000 of the aliens would, of these alien civilizations would be in exactly the right place. 1 in 3,000. So that was a little bit of a simplification. Of course, stars, as I mentioned before, are really far away. So we don't see a picture like that one that I was showing. That was a picture of the sun, and I was drawing the Earth to scale. But in reality, stars are much smaller than any pixels we can make. They're so far away, they're just a little tiny dot that's unresolved. There are a handful of stars where we've been able to image them a little bit more precisely. But in general, we basically just have a dot. And so what's happening is the Earth is transiting over there, it's crossing in front of the star, so is Jupiter, all this kind of stuff. But we can't resolve that. We can't like see that little dot. Instead, what we see is we see the brightness of the star, and the star gets fainter for when the planet's in front of it, and then it goes back to being bright again when the planet leaves. And you can work it out. It's basically just geometry, how that works. It's like a little black disk crossing in front of a bright disk. And what ends up happening is you end up with a signal that looks like this. So this is what the Earth would look like in a perfect world. This is what the Earth would look like when it was crossing the sun from an alien looking at it with the transit method, who just happens to be lined up in exactly the perfect orientation. Now, I mentioned that this lasts for 13 hours. So that's roughly what we have there, and it happens once a year. And so, and the detailed shape of this we know very well, because like I said, it's basically just geometry. But in order to see this, we have to be lucky, be in the right location, and we have to be looking there at the right time. So most of the year, it would be super boring, and then we just happen to be looking at it at the right time. And if we're looking for Jupiter, then we have to be even more lucky, because we have to look at the star for 12 years to even see it happen once, right? Unless we're really lucky, and it just happens at exactly the right time. So these are some of the things that we need to do. Oh, another thing I wanted to comment about here is that this is drawn to scale. So the size of the change of the brightness is proportional to the area ratio of the star to the planet. So it goes like the radius squared of the planet. And so the Earth only changes the brightness of the sun by about 100 parts per million. And so that's a pretty small signal that happens for a short time, only once a year. And so the things that we need to be able to do is we need to be looking at the right place, the right star, at the right time, and we have to be measuring the brightness of that star very, very precisely, or the relative brightness at least. And so another way of doing this, we have to be looking at the right place at the right time, but maybe we could look at a lot of places for a lot of time, and maybe we'll get lucky. And so that was the point of the Kepler mission. This is what Kepler looked like, or an artist's rendition, I guess. And it was a satellite that was launched in 2009. Like I said, it ran for a little over 4 years before it failed, mostly failed. It's still running a little bit, but we're not going to be talking about that today. We'll just talk about the main mission. And this satellite is orbiting the sun. And so it's pretty far away from us. And what it does is it just looks at one patch of the sky continuously for the 4 years that it was running in its normal mission. And inside of that satellite, there's a CCD, just like you have in your iPhone or something, but many orders of magnitude more expensive. Looked something like this right here. But basically the same principle. It's just a bunch of pixels, measure photon counts, and take a video. And so it looked at this part of the sky, which was chosen very specifically to have lots of stars, but not too many stars. This is what a typical frame from the telescope looks like. So there are about 3 million brightish stars in this field right here. But remember, I said that the satellite is orbiting the sun, so it's really far away from Earth, and so actually downloading the data is really expensive. So we can't actually download all of the pixels. In fact, we can only download 5% of the pixels that are on this frame right here. And so once every few months we would download a full frame like this, but in general we would only download the little patches around 150,000 stars in this field right here. And we would get it at a frame rate of about 2 frames per hour. Part of the reason for that slow frame rate is the downlink cost, and another part is that stars are faint, like I mentioned before. And so we actually have to take long exposures to get enough signal to measure them as precisely as we need to. Remember, we want to pick out 100 parts per million changes in the brightness. Yeah?
Do you use any compression technique to kind of make it smaller in size, like images?
Yeah, I assume that they do. I actually don't know specifically what they do. It's integer data. So it's not like that's not a huge. I'm not sure how much you could do, but I'm sure they do something. Yep.
Was the Kepler satellite in a geosynchronous orbit, or was it?
No, so it's orbiting the sun.
Okay, so.
And so it's at L2, so it's about the same distance from us as the sun is from us.
I'm assuming you also have to correct for the tracking as well.
Yeah, so the reason why the satellite failed was actually because of pointing, and I'll demonstrate that in just a second. But yes, it was pointing at.
Using that data, by the way.
Sorry?
A friend of mine was also using it.
Okay, yeah. It's one of the things that's great about this data set is it's actually all public. So I'm not an official member of this team. I do collaborate with a lot of official members, but this is just available for download. And I have a Python module that downloads it for you and gets it in nice format and all that kind of stuff. But
You're going to show us, right?
yeah, I'll demonstrate that at some point. Yes?
I guess 2 things. One, outside of planets passing in front of stars, what other things can modulate the brightness of stars?
That's the point of this entire talk. Yep.
Number 2 is there no kind of simple hadron collider type early detection, so they don't even have to capture and store meaningless signals?
So that's a really interesting question. No, with this one they basically preset the stars that they were gonna focus on, and that decision was based on which stars are kind of like the sun, because we wanted to find solar system-like things. But one of the reasons why you wouldn't want to do that is, remember, these signals happen so infrequently and they're very low signal to noise. So basically you want to see the planet cross at least 3 times before you're confident that you have everything. And you need the 3-4 year baseline in order to get that in the first place.
It's not that you can upload functions or programs to the satellite. The satellite is just a camera.
Yeah, exactly. And actually the software is very specific about when we were trying to figure out what to do with the second round of the mission. The constraints are pretty crazy, but it might be worth talking about that more offline. But basically they have to fix which parts of the CCD they want to read out. Yeah. Great. Okay, so like I said, the actual frames don't look like this. Instead, this is what the data actually look like right here. So this is a movie, actually. I don't know if you can see that. There are actually 5 planets in this movie. You probably can't see those either. So what's happening here, this is a little cutout. This is like if you zoom in too much on Photoshop, right? Each of those squares is a pixel on the detector, and this is a fairly typical star that's downloaded. And I've sped it up a lot, but this is about 3 months of data that I'm showing right here. And what you can see is that it's sort of, I said before that they're little points. They're so tiny that we can't resolve them, but it looks like it's taking up a bunch of pixels right there, and that's due to diffraction and optics and all of those things that you might remember from, I don't know, junior high or something. But another way of plotting this same movie is as a time series like this. So here along the x-axis I have the time, and then the y-axis is the brightness in all of those pixels. And so the pixels that are colored black are the ones that are dominated by the star. But there's some interesting things going on in this figure that I wanted to point out. So I'm going to try to walk over here and not disconnect the microphone. So one thing that you can notice is with time, it looks kind of like the star is moving up and then moving back down again. Right here you can see that this one's getting fainter, this one's getting brighter, and then vice versa. And that's due to pointing of the telescope. So the telescope is jittering a little bit, but it's actually pointing to better than a hundredth or a few hundredths of a pixel. So we got this like crazy telescope out there with these pixels, and it's able to lock right onto the stars and point perfectly. And that's very important. That's what went wrong. That's why it's not running in this same format anymore. Another thing that you can see is, you maybe noticed before in the movie that there's another star over here. That's an issue. There's contamination across here. But either way, what we can do is we can use these pixels and sort of measure the brightness of this star, the one-dimensional brightness as a function of time. Yep?
What's up with the gaps?
Yeah, so what happens is it actually downloads once a month. And the way that it downloads, they didn't want to have any moving parts on the satellite, so they decided that the way that they would download is by taking the satellite and pointing the main camera, or right back at Earth. So it points to Earth, downlinks, and then goes back up once a month. And this is 3 months of data right here.
And it can retract right to the exact same.
It's unbelievable. Yeah.
Well, that's why the motors fail.
Sorry?
That's why the motors fail.
Maybe. I mean, they were. The initial mission was only supposed to be 3 years, so they did complete what they were expected to do. But yeah.
Why are the bands wider on like some of those?
Yeah. So the scale on the y-axis is arbitrary. I've just sort of scaled it so that, so you're seeing more noise in the faint pixels. So the star was bright, and then the faint one you just see. That's just counting noise. So that's the kind of thing that we have to deal with right here. So now if we take this data and we just measure the brightness of that star, we get something that looks like this. This is the brightness as a function of time. And this is our sort of best estimate of what that is. And like I said, there are 5 planets in here. Does anyone see them? No. Maybe some people do. But there's some crazy things going on here. So the planets are right. This is a planet right here, and there's one right here. Okay. So these big trends aren't the planet. That's actually the star varying. So all stars have spots on them. They have flares. They're these like big convecting balls of gas, right? So they're very active objects. So actually, there's a lot of crap going on that's a lot bigger than the transit signals we're looking for already, right? But then there's also a little bit of the motion of the satellite still imprinted on this, and lots of other things going on. And there's just that intrinsic thickness that's due to just the counting noise in the detector. And so remember, we want to look for, so this is in parts per million again, we want to look for things that are about 100 parts per million and measure those in this. So we can see that it's going to be a bit of a challenge, right?
And you're looking at the quantum limit, like the photons?
Yeah, so actually photon counting noise is one of the major effects. Yeah. So this everyone should gasp, because this is the best, most precise brightness of stars ever measured, or most precise measurements of brightness ever, basically. So what's the connection between this beautiful model that I showed you earlier and this crap we're getting on the top that's like the best measurement that money can buy? So what's going on? We have our data is over here on the right, and there are a bunch of factors that are coming in to cause all these things that are going on. So there's the signal, the thing that we're looking for. The star is doing some things. And then there's this counting stuff that I was talking about. And there's some other issues with the sky level and things like this, but that's not too important for today. And this variability, this trend here, is due to astrophysics, so all of the activity in the star like I was talking about, but also the wobbling of the spacecraft itself. So we've measured our data, so we have that. We know what our signal looks like. It's basically just geometry. I'll be right there. we can basically estimate what the noise level should be pretty well. But what are we going to do about this variability? Question?
So the data points, if you have a 15-hour transit time, and you have like 1 frame every 2 hours, do you normally see that many data points?
It's 2 frames per hour, but yeah. And so yeah, this is about typical for that. Yeah, that would be right. So there, it's something like 24 frames that account, 22 frames that account for this. Yeah, but remember we did it for 4 years or something, so but it's a handful of the data points, and the full stream, if you work it out, is something like 70,000 data points, and only about 100 of those are actually the signal that we're looking for. Yeah. Okay. So one of the reasons why this is hard is that we don't really have a deterministic model for what's going on. Stars, like I mentioned, are they're these very active, complicated things. They're hard to, we understand them pretty well at sort of a high level. But actually simulating a single star, the way that it works is you would cut out a little patch of the surface and put this onto a huge computing cluster and run for 6 months, and it would, you'd have like 10 seconds worth of simulation for what happens on the surface of that star. And probably all the physics is wrong anyways. And so that's hard. But then there are also these effects of the satellite that we can't really measure at very high precision, and all of these other things. So there's a lot of stuff going on, and we don't have a deterministic model for it. So how do we clean up all this crap? So the standard thing that people do, astronomers love to invent things, invent techniques, and just hack at things. And so the standard thing that you would do is take your data. There's sometimes a little regression step where you try to regress out some other light curves from other stars. That's not so important, but then they finish by running a running windowed median filter and just trying to remove all of that noise. And of course, there's some choices about how long that scale should be, and whether or not it actually affects your signals and all that kind of stuff. And it does, in fact, distort your signals and introduce all sorts of correlated noise and all of these issues. But it does pretty well. So for this particular star that I was showing earlier, here's the paper that was studying this star right here, and they've filtered all of the light curves, and they've found these transits, and then these are models of the 5 planets in that system. And so this is kind of what we're working with here. But that works pretty well. And we've found, like I mentioned before, we've found thousands of planets. And so here's a plot of some, as of yesterday, the confirmed planets discovered by Kepler. And what you can see is there's lots of them. The blue points right there, and along the x-axis I have the orbital period, or the length of the year on that planet. And then the size of the planet is on the y-axis. The black points are the 3 planets in the solar system that would appear on this plot. So we have Mercury, Venus, and Earth. And you can see that they look like outliers from this distribution, right? And so it's possible that our solar system is just really rare, that they are actually outliers. But I have a pretty strong prior that it's not that rare because I live on one.
So what did Jupiter and Saturn and those planets look like on Mars?
So they would be on much longer periods, right? So this ends at a year and a half, right? So yeah, so it would fall off. But and also they're bigger as well. But they would also look like outliers. So why is that? I mentioned earlier that exoplanets are hard to find, and it turns out that small exoplanets are harder to find than the big ones. And the reason why, of course, is that this is the Earth to scale on the sun. You can see that there are all sorts of spots and stuff that are bigger. All the noise is bigger than this thing. And so, the signal strength scales like the radius squared. So small ones are a lot harder to find than big ones, right? And it turns out that small planets on long orbits are even harder to find, because remember, you have to be looking at the right time, and so you have to be lucky. And actually, in the standard data analysis pipeline for this, they require that there are 3 transits seen for a planet for it to even count. So there's nothing longer than sort of a year and a bit. in the data set. So Jupiter, for example, we haven't found any Jupiter analogs in this data set because you would only ever see it once, and it would be big, but it's easy to confuse that with all the other noise that's going on. And in fact, you can quantify this. So this was great work by a grad student at Berkeley who went through and characterized how hard it is to find planets. And Earth would be sort of in the bottom right of this figure right here, where you can see the survey completeness. So when it's white, you find everything. So we can comfortably say that we've found all the planets up there, with a few caveats. But at Earth, it's basically 0. And so so what it looks like is that there's some selection effects that are going on right here. That doesn't stop us. Lots of people extrapolate. I published a paper a few months ago that estimated how common Earths are. And they're not super common, but they're pretty common. And I estimated that there should be 10 transiting Earths in the data set in hand. And so now I've set out to find them. And so the title of my talk was about Gaussian processes, and we're already more than halfway through, and I haven't even touched on that yet. I'm really sorry about that, but hopefully some of this data stuff was cool. But this is where we start getting into the time series analysis that I promised. So I'm not here today to teach you too much about what Gaussian processes are. Mathematically, I will touch on it briefly, but this is the standard reference if you're interested in learning about them. It's a free textbook. You can Google Gaussian process textbook. It's got all the things. It's great. PDFs online. Now, so I showed this figure before. This is the generative process for our data, or so we say. And what we want to do is we want to model the things that we don't understand somehow. And this is where the Gaussian process comes in. We rearrange this equation right here. We take our physical model of the thing that we know that we're looking for. We move it over to the other side. And then we end up with just this crap that we don't know over here. And we're trying to model that with a Gaussian process. So what is a Gaussian process? There are lots of different ways of describing it. Describing what a Gaussian process is, but one is that it puts a probability distribution over smooth functions, and this probability distribution is tunable. It has some choices in it, and here is an example of, I think, 12 functions that were drawn from a particular Gaussian process distribution right here. And so you can see they're all smooth, they're all infinitely differentiable or whatever. But you can see that they have sort of a characteristic, they have some characteristic scales in here. So the width of that, sort of the strength of this variation in the y-axis here, they're all sort of roughly the same. And then the length over which they're smooth like this is also the same for all of these, okay? So this is an example of a Gaussian process. So we can change these parameters. So if we shorten the length over which they're smooth, then we get something that looks like this. You can see they're kind of wild. And then we can also change the variation like that. So this is sort of the simplest example. We have 2 parameters and we can play around with it. So this one that I showed at the beginning, that kind of looks pretty similar to the data that I was showing before, right? So that's kind of cool. The thing that's nice about it is, it might go up or it might go down, and we don't know, because we don't understand stars. But we might be able to say that, that it should sort of vary with some characteristic time scale. As physicists, we love to do that. Right? So this might be an effective model for the things that are going on. So if we take this and just fit a Gaussian process to it, we get this line right here. This line actually has some width to it. It's a probabilistic estimate for what the star is doing. And you can see that, that looks pretty reasonable. Now, what does all this mean? Why is it called a Gaussian process? We don't need to go into the details here, but mathematically the story is that your data points are a single realization of a multi-dimensional Gaussian, where the dimension of that Gaussian distribution is the number of data points that you have. And so that's a really crazy thing to visualize. So in my data sets, it would be a 60,000 dimensional vector is what my data are. And so that's sort of a little bit hard to grasp, and that might be a discussion for beers later. But mathematically, what that looks like is this. So our data, y, are drawn from a normal distribution with some mean function evaluated at a bunch of times, where this is my model of what a transit should look like. And then all of those points are covariant with each other through this covariance matrix right here, which is this 60,000 by 60,000 matrix. Now, how do we describe that? The standard, the way that it works in a Gaussian process is you write down some function that gives you the elements of that matrix, right? And so that's called the covariance function or the kernel function. Oh, I meant to show this, but so right here you just have some function that takes in 2 times and it says how correlated they are. And this is where sort of the magic comes in. This is how it all works. But then mathematically that equation that I showed on the previous slide is this. And some people just walked in and saw this on the slide, which is a little scary. But it doesn't matter too much, the details that are going on here. I'll come back to that in a minute. But this is the equation that you need to evaluate if you're going to fit. So we have some parameters that describe this function right here. So for example, in the example that I showed earlier, that would be like the length of time that the function was smooth. And then also the amplitude of the variations would be 2 parameters that would go in there. But then I also have the parameters of my planet and that kind of stuff.
IMJ are different times for the same stuff.
Exactly, yep. So like I said, the choice of this function is where all the magic happens. So here, this is the function, this is the covariance function that I was plotting earlier. So you can see here, the problem with this is it kind of looks like a Gaussian, but we already have overloaded Gaussian in this case. So this is called the exponential squared kernel, or the squared exponential kernel. And it right now just has 1 parameter. So it has the length of time over which the points are correlated. And you could just multiply that by some factor that was set the scale of the variations. The covariance matrix that you would get from something like that looks like this. So as points get closer together in time, time is along the x-axis and the y-axis here. So the point with itself would be along the diagonal, and nearby points are correlated, and as you get further away, they're uncorrelated, right? So that's sort of the simplest thing. We just have the 2 parameters in this one. You can do way crazier things. So here's an example of something else. If you think you have some periodic oscillations in your signal, but they're maybe not totally coherent, then you could write down something like this right here. It has a bunch more parameters, including the period. And the covariance matrix would look something like this. So this is the standard example that's given in every Gaussian process demonstration. This is the CO2 levels on the top of Mauna Loa in Hawaii as a function of time. And what people do is they use a Gaussian process that has 20 parameters or something and extrapolates this function, so predicts into the future. And that would look something like this. And this is kind of cool. This is useful. So that it gives a predictive model without, you're not imposing too much structure on this. You're just writing down what the covariance between the points are, but you can predict what this is going to do in the future. And you can see that the prediction gets more uncertain as we get far into the future. And so that's kind of cool. But we won't talk about that too much. That was just to show. Now, so I showed this slide before. And I said that this is all you have to do. This is the whole thing. This is what a Gaussian process is. And that's true. So here is an example of how you would code this up in Python. This is more or less the most efficient version that I could come up with using the standard library. And we have some function, the kernel function, that evaluates the covariance as a function, for two different points. Okay. And so I also have written some code that can do this, that basically inside does this, but evaluates the kernel in C, so it's a little faster, and this same function would look like this. All right, so that's cool. So we can implement this pretty easily. The code is called George. It's down there, but I'm going to come back to that in a minute, so don't worry about that too much. Here's just how expensive this is. This is the size of the data set that we're working on, and the time it takes to evaluate this model. Basically, scikit-learn sucks. It's not. Anyways, we'll talk about that later. But so this is my code right here that's running this benchmark here. But remember, I said that my data set is 60,000 data points, and so we're already getting pretty expensive here. Things are starting to if I actually want to put this into an optimizer and evaluate it a bunch of times and actually fit a model, then we're going to run into some issues. And so this, I hate all this shit, but I heard a definition of big data the other day, which I kind of liked, which is data where you have to care about the scaling of your algorithms. And so in my case, this starts to come in handy, even though, compared to lots of people, my data is pretty puny. But it does matter, the scaling of the algorithms. And so the standard implementation, the thing that I showed previously, scales like n cubed, so the number of data points cubed. And that's because you have to evaluate the inverse of this gigantic matrix, which is something like n cubed. We also have to compute this determinant term. And that's relevant because all standard linear algebra packages don't do that. So if you read the LAPACK documentation, for example, in the first page they have a bold warning that says never compute determinants. It's a really stupid idea. No one would want to do that. But I need to do that. So I went across the street to the applied math department, asked some folks what I should do because my model wasn't working and it sounded really sick. And they said some words that I didn't understand, and I asked them if they could compute determinants, and they said absolutely not. That's a terrible idea. Why would you want to do that? But then they went away for a few days and came back and had figured out how to do it. And it turns out that we could implement this. So the basic idea is that there's some structure in these matrices. They're smooth, and so we might be able to take advantage of that structure to evaluate this model a little faster. And so don't need to worry about this, but the thing that's cool is that the scaling of this algorithm is n log squared n, which is faster than n squared. Everyone gasp. That means it never touches every element of the matrix. Let's talk about that later, but this is really cool. It was implemented in this GitHub repository in C++. And this is what the code looks like. It's applied mathematicians writing, so it's a horror. But I did the hard work of wading through this and bringing it into writing Python bindings and this kind of stuff. And now it sits inside of my code. So this is the example that I showed previously. And you can just add this one little flag, and then it suddenly uses this n log squared n algorithm. And here's what you get for the scaling. And even for small matrices, it does a pretty great job. And so this is really cool. This is why you would maybe want to use this code and this algorithm. And it works very well for modeling exoplanets. This has actually been used in 3 published astronomy papers so far. And this just came out a few months ago. So it's very exciting. And here, I think I'm at the end of time. So here are the links to the info, and I think we'll take questions. Yes? Yeah, so that's a great question. So it was about another package called GPy, which is from University of Sheffield, I think. And it's it's the place where all the sort of top of the line inference algorithms for Gaussian processes are implemented. And so it's slower than my code because it's not built on top of this linear algebra package. So it would scale like, doing the trivial things like the simple scaling there. But it has a lot more flexibility. So it does actually implement more algorithms. So if you have a smallish data set, it might be a good thing to use. But most of the basic things would be the same. And actually, the way of specifying kernels is very similar. Yep.
What is your kernel function?
Oh yeah, I think I might even have internet access here. So there's documentation.
For your data set in particular.
Oh yeah, so I'm using the Matern 3.2 is my standard go-to.
Is there some sort of kind of theoretical justification based on your model, or is that just from the structure of your data?
Yeah, so there isn't really. It's just a simple example of something that's smooth with some length scale. And I've found that, so one of the things that's nice is that we care about a specific thing, right? So we care about the properties of these planets. And so we can take real data that don't have planets in them, put in fake signals, and see how well we do. And in practice, the Matern does the best of the standard kernels. Yep.
You mentioned the whole thing about filters and
Yep.
brings back memories. Now, here's, did you have to apply any type of window Fourier transforms for your data analysis?
No, so I don't ever do that. I directly model the raw photometry in the time domain, and yeah, so that's pretty cool. Yeah.
So you're saying that the algorithm that you're using to compute your covariance function is also amenable to a kernel besides squared exponential code? Was the example you're using?
Yeah. Yeah, so the scaling that I showed was for the Matern kernel, actually. But yes, so the sort of factor out front depends a lot on which kernel you choose, and it depends on the dimension of your input space. So it works really well for one-dimensional data, and it scales really badly with the number of dimensions. And so yes, it will. But I mean, the scaling is the same, but the constant factor quickly blows up. Yep.
What do you use for an optimizer?
So I actually don't normally optimize. I always sample, because that's my jam. But I use SciPy minimize, and it works like shit. It's terrible, but optimization is hard, right? So, and so you have to be somewhat careful with that, of course. Yep.
So you predicted 10 Earths in the data set. How many have been found?
So none have been found, and this is the disclaimer I should have put at the beginning. So still nothing has been found. I've only been working on this for a few months, so I don't have any results. They look promising. The motivation for this is that that by not filtering, we should be able to recover, by fitting the star and the planet at the same time, we should be able to recover smaller signals. And that's been possible in synthetic data, but I don't have any real ones yet. Hate to say it. Yep.
Can you talk a little more about your plotting functionality? Is there plotting functionality on this? Because you made those plots,
Yeah.
and that's something that's a little hard for Matplotlib to do these kind of GPU plots where they error bars and stuff.
Yeah, so I explicitly don't do that because I hate having to support that. But in the documentation, I have examples that show how to do it with Matplotlib, and hopefully that's enough for people. But yeah, that's not something that I have in the code.
Did you never have to use what's that? Another software that's very common in astronomy, and I always forget the name. It's 3D archaic.
IRAF?
No, not one.
IDL.
IDL, yeah.
I skipped IDL.
Oh, lucky you.
Yeah. I just started with Python. All right, anyways, thanks. Thanks for that.